Hello and welcome to this video about electromotive force and internal resistance. Hopefully you've watched the video about potential dividers before coming to this. Students really need to be comfortable with the same skills that they need for solving potential dividers. So that is how to use a voltmeter and an ammeter to calculate resistance for a range of components. They also need to be familiar with the ratio understanding of potential dividers, and they need to be familiar with how to calculate y-intercept and gradients for y equals mx plus c style graphs. What is an electromotive force and how does it relate to internal resistance? Before we answer this, ask students if they've noticed that whatever setting they've got on their power supply often doesn't seem to be the same as the reading they're getting on their voltmeter. Have they thought about why this is? The simple answer is that any normal power supply or battery has got an internal resistance. And that means that it itself will be heating up a little bit and it's not giving all of the energy to the components that are in the circuit. Electromotive force is defined as the energy per unit of electric charge that is imparted by an energy source. I think of it as a push around the circuit. And as I say, you've got this theoretical maximum, but you're losing some to the power supply itself. Students will often flick on their power supply and expect 10 volts in their power supply and 10 volts on their voltmeter. They will then be disappointed when they plug in a component like a bulb, or in this case a resistor, that the value they get out is lower than they're expecting. So here it's gone down to 7 volts. And they will think that this is a mistake with their equipment. Maybe they've not got a very good power supply. It's not a mistake. It is just the fact that the power supply has got an internal resistance. And once connected in a circuit, there is a voltage drop inside the power supply as well as the potential difference on our load resistor. So let's have a look at why this happens. Why do we get a smaller measured voltage on whatever load resistor, whatever component we've attached to the circuit, than is provided by this theoretical electromotive force? Hopefully, before students do this, they should already have the familiarity with how to solve potential divider questions as a ratio. So, pause this if you need to have a think, but look at the numbers and figure out what would the potential difference measurement be on that voltmeter. Okay, so it's a 20 volt reading that we'd get there because of the ratio 20 to 4, and we've got 24 volts as the input. Now here I've drawn it as a potential divider question. Of course, it's the same theory that will apply for the electromotive force and the internal resistance. It's just that we draw the circuit very slightly differently. That 4 ohm resistor is actually part of our power supply or battery. Normally we draw it enclosed in a single circle, but the physics is exactly the same. And so if we can get our students to understand that that internal resistance is effectively becoming a potential divider, then students will be in a really strong position to figure out why the measured potential difference will be lower than the electromotive force. So I called it the measured potential difference here, but it's also often called the terminal potential difference. Sometimes it's referred to as the voltage out or the potential difference out. So let's go through a series of similar questions. Each time I'm going to tell you what the load resistance is. So here it's 2000 ohms. The internal resistance is 4 ohms. What's the measured potential difference? Pause if you need to. Okay, and the answer is approximately 24 volts. We're going to get most of the electromotive force as the potential difference measured on the load. So we've already done this one. We get 20 volts if we've got a 20 ohm resistance as our load resistor. What about if you have 8 ohms? Pause if you need to. Okay, so it's the ratio of 4 to 8. So in terms of our electromotive force of 24 volts, we're going to end up with 16 volts measured. What about this one? So we've now got a load resistance of 4 ohms and the same internal resistance of 4 ohms. Pause if you need to. Excellent, the answer is 12 volts, so this is literally dividing it into 2. And one final one. So we've got 2 ohms as our load resistor and 4 ohms as our internal resistance. Pause if you need to. And the potential difference we measure is now 8 volts. You can now clearly see that the load resistance has a big effect on what the measured potential difference will be. If you have a very high load resistance, so in our case 2000 ohms, it doesn't really matter what the internal resistance is, we're still going to get the full PD out. As that load resistance decreases, i.e. there's a bigger current flowing through the circuit, the potential difference we'll get out will be less and less and less. And more of the energy will be heating up the power supply or the battery rather than doing useful work in our component. So we can use this information to derive the equation. In this case, we've said we don't know the numbers, but we've got an electromotive force of a capital E. There's an internal resistance of a lowercase r, and there's a load resistance, which is a capital R. And we're interested in what the potential difference measured is across that load resistor. Well, we should be able to figure it out fairly easily. So we've got this theoretical electromotive force, this ideal one there. We've got a potential difference across the internal resistor. And that resistance of lowercase r will have a potential difference of current times R. So the voltage that we measure, the voltage out, is whatever the EMF is, take away whatever the potential difference is on that internal resistor. Understanding how the internal resistance can affect the behaviour of the battery or power supply can help us to make sensible choices about what batteries to buy, for example. So we could compare 2 different batteries. Battery 1 has got an actually larger store of energy than battery 2. But battery 1 also has a higher internal resistance. Now you might instantly think, well, battery 1's better because it's got a larger store of energy, but it depends what you're using it with. If you want to use a battery to power up something like a remote control, well, a remote control has got a really high resistance. So it doesn't really matter what the internal resistance is of the battery. Either of the batteries will work fine with it, and you might choose battery 1 because it's got the larger store of energy, or you might choose whichever battery is cheaper. However, if you've got something like a torch, which has got a really low resistance, well, then you want to have a look at what the internal resistances of those batteries are going to be. If you put a torch with battery 1, you're actually never going to get the maximum brightness. Because of that high internal resistance and the low load resistance, the ratio means that you're never going to get the full potential difference across that bulb. So it helps us to make sensible choices. So battery 1, for example, would work best with a low drain device like a remote control, and battery 2 would work better with a high drain device like a torch. However, it also comes down to other decisions like cost and whether they're rechargeable or not. So we've got our setup where we've got our power supply connected to a voltmeter and a resistor. At the moment, the resistance is the full resistance because I've got this set fully to the right. Let's see what happens if we add in an ammeter. Oh, and the currents can get very high, so make sure you're using the 10 amp setting on your multimeter unless you're certain it's going to be lower than your lowest fuse rating. Okay, so we can now measure the current and the voltage at the same time. And we can perform an experiment where we alter the resistance of the load resistor and we measure how the measured voltage, measured potential difference, and the current change. So let's have a quick go at doing this experiment, but we'll do it badly first of all. We'll do it as a student might do it for first try. What they will do is they'll want to take 6 readings, and they'll go 6 readings all the way from here all the way across to there. So 1, 2, 3, 4, 5, 6 readings. Now we have 2 problems with that if we do it. First of all, when we get down to here, everything stops. And that's because we've had an overload of the circuit. Effectively, we've short-circuited because we've set the load resistance to 0. So let's bring it back over here and do it again. So 1, 2, 3, 4, 5. Now this is a better set of readings. However, we've not got an equal distribution because our first readings were all around 1 amp until they started creeping up here. What we actually need to do is we need to vary it so that the current is changing significantly as well. So not just from 1 to 2, but over a full range of the current values. So let's see if we can get 6 readings. So let's have a go at plotting some of this data. So we've got our 6 readings here, and we can add a line of best fit to this. And now we know that V was equal to the EMF subtract what's sometimes called loss volts, the current times the internal resistance. Now this is of the form Y equals mx plus C. Okay, we've had to be slightly creative with which direction we write our mx and our C in, but we can see that the gradient is equal to the negative internal resistance, and we can see that the y-intercept should be equal to the EMF. And we can just read that off our graph. So it's 9.448. And our internal resistance we need to calculate a gradient for, so let's do that quickly. So we can conclude that our electromotive force is 9.48 volts and our internal resistance is 0.54 ohms. So don't feel too restricted by just putting a power supply next to a rheostat. You can also investigate EMFs in lots of other ways, including batteries. Be careful though, rechargeable batteries can have a very low internal resistance. Here I've created a little battery out of some potatoes using zinc coated nails and copper 2-penny pieces. You could use this to work out the EMFs and the internal resistance, and you'd get a very different result from using the battery. You could also ask students to consider what would happen if you had a bunch of batteries in series, or for example a bunch of batteries in parallel. How would that affect the EMF and how would that affect the internal resistance? To conclude, students can do a relatively simple experiment to figure out the electromotive force and the internal resistance of a circuit. For them to truly understand what's going on, it's best if they fully understand how potential dividers work, hopefully by spotting what's going on in terms of ratios first. If you want to, you can vary the experiment as well by adding in different challenges. For example, a potato circuit or a strawberry circuit works really well. Or you can add in challenges by saying what would happen if the batteries are in series or in parallel.